Hi. In this lecture, we will look at the scientific notation and we will learn how to convert from a decimal to a scientific notation and back to from scientific notation to a number. So, why do we even use scientific notation? Sometimes we have the values for some things that are not really convenient to say in regular way. Let's say we have a dust particle that has a mass of as we call it, 753 nanograms. And if we convert it to kilograms, we would have that many zeros in front. So it's really difficult to, use it in calculations and even, write it in a report. So we would have 0.00000, many times zeros, 753. So it is not really convenient because the person who's reading your report, for example, they would need to count how many zeros you have to have an idea of the exact mass of a dust particle. Or, for example, for a mass of the sun, let's say we have something really huge in mass or in height, or we can use any units in this case, but the idea is something is really high, like a mass of the sun, which is 1,989 octillion. So that's a really huge number that is really difficult to read. So in this case, we would use a scientific notation, which is much more compact. So we have the dust particle and the sun masses here written as in the scientific notation. So a number is written in a scientific notation when it is written as a product of a number k, where k is between 1 and 10, not including, and the power of 10. Okay, so in other words, we have this form k times 10 to the power of n, where k should be a number either 1, 2, 3, 4, 5, 6, 7, 8, or 9. It does not include 10. So this symbol right here, less than or equal to, that means that we are including 1. And this symbol right here, less than, that means that we're not including 10. Okay, and this power can be any integer. It can be a positive integer, it can be a negative integer. For a positive integer, we would have a really big value, so in hundreds or thousands or 100,000s and so on. For the negative value, we would have a really small value, like a mass of a dust particle. Okay, so the mass of the sun can be conveniently written as 1.989 times 10 to the 30th power kilogram. So as you can see, we have that many zeros there, including this three digits as well. So, and for the mass of a dust particle, we have 7.53 times 10 to the negative 10 kilogram. So now how do we convert this number or this number into the scientific notation? So what we need to do is we need to count the number of n, uh, so number of these decimal places that the decimal point must be moved in order to arrive to a number k, where k is, again, as we said, between 1 and 9. So we write it as 1 less than or equal to k, less than or equal to 10. So k should be greater than or equal to 1, but it should be smaller than 10, okay? And then the second step, if the original number is greater than or equal to 1, then the scientific notation is written as k times 10 to the nth power. If the original number is between 0 and 1 as the mass of the dust particle, then the scientific notation would be k to the power of, k times 10 to the power of negative n. So for example, we have a number 5,679. We want to write it in a scientific notation. So first of all, the first value right here, the first digit would be our k, okay? Because it is between 1 and 10, not including, so this number is k. So we need to place a decimal point right after this 5 right here. We will put the decimal point. Now, we move decimal point from the back to from the very back, right? Since this is the whole number, so the decimal point is right here. We need to move this decimal point to this place right after 5. Okay, so we would have 1, 2, 3 places that we move and we count. Okay, the amount of places that we move our decimal point, that would be our n. So in this case, from here, we moved 1, 2, 3. So this is where we need to put our decimal point, and we did it 3 times. So n is equal to 3. Now we have all the information. We know that k is 5, and we know that n is 3. So we can write it in a scientific notation. K times 10 to the nth power would be now 5.6789 times 10 to the third power. Okay, so we usually keep the decimal, the values after the decimal point because they might be useful for converting back and forth. So that's why we keep it. But the decimal point should be written after the first digit. Okay. Now, another example we have here 47 million. Okay, so I want to write it in a scientific notation. Again, I want to isolate first my first digit, that would be my k, right? Because it's between 1 and 9. We cannot take 47 because 47 is it's greater than or equal to 1, but it's not less than 10, right? So we cannot use 47 as our k. But if we use just 4, it's greater than or equal to 1, and it is also less than 10. So this is good, right? So we will use 4 as our k. And now we put the decimal point right after, let me use another color, right after this k, and now we start counting. Wait, so first we have a decimal point at the end, right? But we need to have our decimal point right after 4. So in to put it right after 4, we need to count how many times we move the decimal place or the decimal point from the back of the number to here right after 4. So let's look at that. So we have 1, 2, 3, 4, 5, 6, 7, right? So we want to put the decimal point right here, and we moved it 7 places to the left, right? So that's why our n in this case is going to be 7. And we can write this number in a scientific notation as 4.7 times 10 to this 7th power. Okay, so this is our k, and this is our n. Okay, now another example. We have 0.054 and we want to write it again in the scientific notation. Now, take a look at that. We need to find our k, and we know that k should be a number between 1 and 10, right? So the 0 cannot be a k, right? Because it's less than 1. Then 0, 0 also cannot be k because it again is less than 1. But this 5, it can be a k, right? Because it's between 1 and 10. 54 cannot be k because it's greater than 10. So 5 is a choice for our k. Okay, so that's our k. Now we would need to put, so essentially if we found our k, we need to put the decimal point right after our k, or right after this 5, but the decimal point right now is located here, so we need to move it to this location. What does it mean? We need to count how many times we need to move from the original location to the new location, right? So we would have 1, 2 times. Okay, so we count 2 times, so this 2 is our n. Okay, and now we are ready to write it in a form of k times 10 to the nth power. And as you can see, the original value is between 0 and 1. That means that our n would have a negative exponent, or a negative sign in front of it. Okay, if the value is greater than 1, for example, in this case, right, we had 47 million, then the exponent will be positive. If the value, if the number original value is smaller than 1, if it's between 0 and 1, then the power for the 10 would be a negative. Okay, so we would have here 5.4 times 10 to the negative second power, because we're moving 2 units to the right. Now let's do a couple of practice problems. So first one, we have 432. Now, what is our k? Our k cannot be 432 because it's not less than 10, right? Our k cannot be 43 because it's not less than 10, but our k can be 4 because it's less than 10 and it's greater than 1, right? So k is equal to 4. So that means that we would need to place a decimal point right after our k. So we need to have, 4.32. But now we see that the decimal point originally was here at the end, right? Because we have a whole number, but we want it to be here. So how many decimal places do we need to move our decimal point from the back up to the this position right after 4? We need to move it 2 times, right? So from here, 1, 2. So we want it to be here. So we move it 2 places, and we move it to the left, right? So n is equal to 2. And again, since the original number, let me erase that. Since the original number is greater than 1, then our exponent for 10, right? So we have this is our formula. Our exponent, this n, it will be positive, right? So we can write it as 4.32 times 10 to the positive, positive 2 power, all right? Now the next example is 10,302. All right, our k should be a value between 1 and 10, so it cannot be this 10, so it cannot be all of this number because it's too big, right? It cannot be this value, it cannot be this value, and it cannot be even this 10, because 10 is not less than 10. 10 is equal to 10, but not less than 10. But now if we have smaller, right, so k can be 1 because this equality. So 1 is less than or equal to 1 because it's not less than, but it's equal to, so this is okay. We can use that. So now we would have 1.0302 times 10 to some power. We need to figure out what that power is. So for that, we need to count how many places we move our decimal point from the very back to here. Okay, so it's 1, 2, 3, 4. 4 times we need to move the decimal point till we reach the k. So n is equal to 4, right? So that means that the power for the 10 will be 4. Okay? So we would have 1.0302 times 10 to the fourth power. Okay, now let me erase that. And let's do the other examples. Okay, so now we have 5,432,000. We want to convert it into the scientific notation. So again, our K it's usually the first, if it's not a zero, that's going to be the first digit of a number. So in this case, K is 5, right? Because it's between 1 and 10, not including. Now, N, what would be our N? So since this is a whole number, the decimal point is located at the very end. We want it to be here. So how many places do we need to move our decimal point? Let's count. 1, 2, 3, 4, 5, 6. So N is equal to 6. Okay? So now we can write this number in the scientific notation. We have 5.432, and then you have 3 zeros here, but you can omit them. They're not needed anymore, right? We can write then times 10 to the power of 6. So this value, this number can be written in a scientific notation this way: 5.432 times 10 to the 6th power. Now, let's go to this number and try to write it in a scientific notation. So we have 0.093. Now, again, as we said, K should be a value between 1 and 10, not including, right? So we can include 1, but we cannot include 10. So essentially, it's going to be any value between 1 to 9, right? So it can be 1, it can be 2, 3, or 4, or 5, 6, 7, 8, or 9. So 9, it can also be 9, but it cannot be 10 anymore because in this case, yeah. So it's not 0, it's not this 0, but this 9 it can be, right? So we would have our K is 9. So that means that we need to put the decimal place right after this 9, but originally the decimal point is located right after 0. So we need to move decimal point, in this case 1, 2 units to the right? So our N is equal to 2, but since the value, the original value, is less than 1, right? It's a value between 0 and 1. That would mean that our N would be negative, right? So now we're ready to write the value in the scientific notation. So it's going to be 9.3 times 10 to the negative 2. Okay? All right, so let me erase that, and we will do the last two examples. So we have 0.0000459. Okay, so we want to write it again in the scientific notation. What is our K? K in this case would be 4, right? This is the first value that is greater than or equal to 1 and less than 10. Okay, so that's our K. That means that we need to put a decimal place here. But originally the decimal point is located at the very beginning. So we want to count how many times we move our decimal point until we reach this place, this location after 4. So we have 1, 2, 3, 4, 5. So we need to move our decimal point 5 units. Now again, if we look at the number, the original number, it is less than 1, right? So then our N would be a negative value. It's going to be negative 5. and we can write it as 4.59 times 10 to the negative fifth power. All right, and the last example will be this one, 0.000000008, right? We want to write it in a scientific notation. Again, all the zeros, they do not work for k. The only value that works for k is going to be this 8 because it's between 1 and 10, right? Or 9 if we include. So now we need to find what is our n. As you can see, the value is really small. It's smaller than 1, right? It's less than 1. That means that the exponent for our 10 would be negative value. So now let's count how many times we need to move this decimal point from here, from the original place, up until after the 8, right? So we would have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that means that we have negative 8 places. So we can write this value as 8. You can write 8.0 if you want, or just 8 times 10 to the negative 8th power. Okay, and that would be the same number written in the scientific notation. Okay, I hope that that's clear. Now, next thing is converting from scientific notation to decimal or to the regular numbers. So now to do that, we need to determine the exponent n on the number of the number 10. And if this n is positive, right, as we had right here, where was that? Like this one, right? So if our n is positive, then we move the decimal point n places to the right. If it's negative, then we move the decimal point to the left. Also, we add zeros if we need, if we have some empty space, right? So let's say we have this number written in scientific notation. So we have 2.3 times 10 to the third power. It is the same thing as saying 2.3 times 1,000, right? So 3, the third power means that we have 3 zeros, okay? So you can calculate this on your calculator, or we can just move the decimal point 3 units to the right from here. We did that before, right? So we start from here and then we move 1, 2, 3, right? So all the empty spaces we fill up with zeros, and this is how we get the final answer of 2,300. Okay. Now the next example is 4.48 times 10 to the negative fifth power. So remember, if we have n to be negative value, that means that the original number would be really small. It will be less than 1, but bigger than 0. And you will see at the end that it is, in fact, a really small number. So what it means in this case, 10 to the negative fifth power, remember we said that 10 to the negative nth power is the same thing as 1 over 10 to the positive nth power. So in this case, if we have here 5, that means that we have 5 zeros, right? So we have 1, 1, 2, 3, 4, 5 zeros. So we have 100,000, right? So it's 1 over 100,000. And we have 4.48 times this 1 over 100,000. We don't have to write this step. Where's that? Yeah, you don't have to write this step. You can just straight away from here move your decimal point either to the left or to the right. So here you would move it to the right. In this case, when n is negative, we move it to the left. So how many units we move this decimal point to the left? Exactly, we move it 5 units. So we start with this 4.48, right? And then we start moving 1, 2, 3, 4, 5, right? And all the empty spaces we fill up with zeros. Okay, So in the regular notation, we would have the answer would be 0.0000448. Okay. So this is the essentially this number is equivalent to this number. These are two same values. Okay, let me write it here probably. Okay. Now another, we have several practice problems. So let's try those. So first one is 3.1 times 10 to the second power. Again, when we have n is positive, then we move our decimal point 2 units to the right. So we start with 3.1 and we move this decimal point 1 2 units to the right. So we fill up all the empty spaces with zeros, and we have the answer of 310. Okay. Another example is 9.02 times 10 to the negative 1. So again, we look at the n, it's negative, so that means that the decimal points should go to the left 1 unit, right? So we start with 9.02 and we move our decimal point 1 unit to the left. So it's going to be here. So we will have 0 here, and if you want, we will have a decimal point here, and if you want, you can put 0 in front of it. If you don't want, you can keep it like that. Okay, so then next one, 2.6 times 10 to the 5th power. Again, n is 5, which means that we need to move our decimal point to the right 5 times. Why to the right? Because our 5 is a positive value. If it's positive, we go to the right. If it's negative, we go to the left. So we would have 2.6, and now we start moving the decimal point. 1, 2, 3, 4, 5. So that's going to be here. And we fill in all the empty space with zeros. Okay? So the answer would be, in this case, 260,000. And that's it. All right. What about 2 times 10 to the 0th power? So remember that any power, or I mean any number to the 0th power, that's just 1, always. This is the rule. Okay, if we have, let's say, 2 to the 0th power, that's 1. If we have x to the 0th power, that's 1. If we have, I don't know, 5,007, for example, to the 0th power, that's also going to be 1. Okay, anything, and also 1 to the 0th power, that's 1. 10 to the 0th power, that's 1. A million to the 0th power, that's 1. Everything to the 0th power is always 1. So in this case, we would have 2 times 1, which is just 2. So we keep it as it is. Okay, so in this case, the scientific notation and the regular notation, they don't have any changes in this case. And the last example is 4 times 10 to the negative 4th power. So let's look at that one. Our n is a negative number, it's negative 4, and the decimal place point is located at the end of the 4, because 4 is a whole number, right? So in this case, we would have 4 with the decimal point at the end. Now, since n is negative value, we need to move to the left, right? We need to move our decimal point to the left 4 units. So let's start. 1, 2, 3, 4. So this is the location, the new location for our decimal point, and we fill in the empty spaces with zeros. So the final result would be 0.0004. Okay, this is how we write the scientific notation, convert scientific notation into the decimal. All right. So the last thing I want to show you is multiplication and division by using scientific notation. So one important note that you need to remember is this rule here, the 2 rules. So any number to the power of m times the same number to the power of n can be written as that number to the power of m plus n. So in case, let's say we have 2 to the power of 4 times 2 to the power of 5, for example. That can be written the same way as 2 to the power of 4 plus 5, which is 2 to the power of 9. Or if you, let's say, have 3.1 to the power of, I don't know, 2 times 3.1 to the power of 10. So in this case, we would have 3.1 to the power of 2 plus 10. That's going to be 3.1 to the power of 12. Okay, so the base, this number, that should be the same. The powers can be different. So when they're different, we just add them. Even if you have something like, I don't know, 3 to the power of 4 times 3 to the power of 4, we can write it as 3 to the power of 4 plus 4, which is 3 to the power of 8. Okay? So the number should be the same. This number, the base should be the same. Okay. The same goes for the division. If we have a number to some power divisible by the same number to another power, we just subtract the powers, right? So if we have, for example, something like 2 to the power of 3 divided by 2 to the power of, let's say, 7, for example, right? Or we can write it like that in the fraction form. That would be written as 2 to the power of 3 minus 7. So in this case, the 3 minus 7 would be -4, and we have 2 to the power of -4. If you want, you can keep it this way. If you want, you can write it in with a positive exponent, but just make a reciprocal, so you would have 1 over 2 to the fourth power. Okay? So this is kind of explanation of this rule. So now, if we have the two numbers that we want to multiply, so let's say we have 3 to the power, 3 times 10 to the power of 2 times 2.5 times 10 to the power of 5. So what we need to do, in this case, we would need to multiply 3 and 2.5 separately, and then we multiply 10 to the power of 2 times 10 to the power of 5 also separately. So in this case, we would have, we can just regroup these these four numbers. Because there is a multiplication, it doesn't really matter what you multiply first or second. So in this case, we will group 3 times 2.5, which gives you 7.5. And then separately, we multiply 10 to the power of 2 times 10 to the power of 5. And again, we apply this rule. You see that 10 and 10, these are the same values. So we can just write them as 10 to the power of 2 plus 5, right? Which gives us 7. So this is going to be the final answer for this multiplication. Now, another example would be 4 times 10 to the -2 times 6 times 10 to the 8th power. Now, we combine 4 and 6 together and multiply them together. So we have 4.6, which is 24. And we combine the powers, 10 to their powers together. So we would have 10 to the power of -2 times 10 to the power of 8. And since, again, 10 and 10 are the same numbers, we can combine them and we can just add the exponents. So we would have 10 to the power of -2 plus 8. Since this was negative, we keep that negative. So we have negative plus 8. And in this case, we would have 10 to the power of 6, right? Now, since we have 24 times 10 to the power of 6, remember that the rule is k times 10 to the power of n. And k should be a value between 1 and 10, right? But 24 is greater than 10, so 24 cannot be k. But what can be k? K can be 2, right? So we need to convert this 24 in the scientific notation. So that means that we would need to do some manipulations with this power of 10 and with the decimal point. So essentially, right now we have a decimal point located right here after 4 because we have a whole number, 24, right? But we want it to be here as 2.4, right? What does it mean? We need to move the decimal point 1 unit to the left, meaning that we need to add one more power to the existing power, right? So to the power of 6, we add one more power as we move from the original location of the decimal point to the new location, right? We add 1. So in this case, the new number in the scientific notation would be 2.4 times 10 to the 7th power now. Okay, now let's do a couple of examples for practice. All right, so we have here 3.2 times 10 to the negative 3 times 4.8 times 10 to the negative 4. So how can we combine this? So we would have 3.2 times 4.8 in one parenthesis, and then we would have 10 to the power of negative 3 times 10 to the power of negative 4 in another parenthesis. So 3.2 times 4.8 is going to be what? So we would have 3.2 times 4.8, that's going to be 15.36 times 10. Again, since these are the same bases, we can just add the exponents and we have negative 3 plus negative 4, right? Keep the negative for all of the powers, right? For all of the exponents, just add them. So now, negative 3 plus negative 4, that would be essentially negative 3 minus 4, which is negative 7, right? So we would have 15.36 times 10 to the negative 7. Yes? So again, look at this value. It's 15, right? It cannot be k. K can be anything that is smaller than 10. 15 is bigger than 10. So if we choose 1 to be our k, that works, right? So we want 1.536 times 10. Now, our original decimal point was located after 5. So let me write it here. And then we need to move it 1 unit to the left, right? So when we move 1 unit to the left, we would need to add 1 to our power. So we have negative 7. Now we need to add 1 as we move from the original location of the decimal point to a new location. We add 1 to that, and this new answer becomes 1.536 times 10. Now, negative 7 plus 1 is going to be negative 6, right? So this is a correct answer for this multiplication. Okay, now let me erase this. And let's do now this problem. So we have 3 times 10 to the 4th power times 2 times 10 to the 3rd power. So we combine 3 and 2. So we have 3 times 2 in one parenthesis, and we have 10 to the power of 4 times 10 to the power of 3 in another parenthesis. So we would have 3 times 2, that's 6, times 10, and now we would just add the exponents. 4 plus 3, that's going to be 6 times 10 to the 7th power again, right? So since 6 is a number between 1 and 10, we can keep it as it is. So because this is our k, right? So everything is fine. We don't need to move any more decimal places anywhere to the left or to the right. So this is good already in a good form. So the division is performed the same way. The only difference is that instead of adding the exponents, we are subtracting the exponents when we divide, right? So essentially what we have, we can combine these two. 6 divided by 2, we would have 3 in this case, and then separately 10 to the 6th power divided by 10 to the 2nd power. We just subtract the exponents, and we have 10 to the power of 6 minus 2, which gives us 10 to the power of 4. And that's it, right? We don't need to move to do anything else with this expression. Now the second example would be 2.4 times 10 to the fourth power divided by 3 times 10 to the negative second power. Again, we divide the numbers separately and the 10 to their powers separately. So 2.4 divided by 3, that's 0.8, and 10 to the power of 4 minus negative 2. So here you see we have a negative with our 2, but we still need to subtract. So this is the division, essentially, what we're changing the division to, but the negative 2, we keep it, okay? Now, we know that negative times negative will give us positive. So we essentially have here 4 plus 2, which gives us 6, right? So we have 10 to the 6th power. Now, 0 cannot be k, because k should be a value between 1 and 10, not including, right? 0 is less than this 1, so we need to choose k to be 8. That means that we need to move our decimal point 1 unit to the right. When we move it to the right, we need to subtract the 1 power from our 10 to the 6th power, right? So as we move the decimal point to the right, we subtract at the same time the 1 power from the 6. So we would have 8 times 10 to the 5th power. Okay, now let's do a couple of examples as a practice. So we have 8 over 2 times 10 to the 6th power divided by 10 to the 1st power. So we would have 8 over 2, that's 4, times 10 to the 6th power minus 1, which gives us 4 times 10 to the 5th power. So 4 can be k, so everything is fine. We don't need to do anything. This is the end for this example. Now, next example is 5 times 10 to the negative 2nd power divided by 8 times 10 to the 2nd power, positive 2nd power, right? So we combine 5 and 8 together. So 5 divided by 8 times 10 to the negative 2 divided by 10 to the positive 2, right? So we would have, so 5 divided by 8, that's going to be 0.625 times 10. We have negative 2 minus this 2, right? So we would write it as minus 2. So we have, in this case, 0.625 times 10. Negative 2 minus 2, that's going to be negative 4. But now, as you can see, the 0 cannot be k, so we need to move the decimal point to the right until we have a value that is between 1 and 10. So 6 is a good candidate for k, so we would have 6.25 times 10. And now we have negative 4 here, and as we were moving from the decimal point from here to this location, new location, right? So from here to new location to the right, we need to subtract 1 from the power. So subtract 1. And in this case, we have 6.25 times 10 to the power of negative 4 minus 1. That's going to be negative 5. And this is the final result for this example. Okay? Now, the last example is the following. Let me copy that. So we have 3.6 times 10 to the power of negative 7 divided by 7.2 times 10 to the negative 3. Now we combine the numbers together and the tenths together. Times 10 to the negative 7 over 10 to the negative 3. And we have, so 3.6 divided by 7.2, that's going to be 0.5, times 10 to the power of negative 7 minus negative 3. So don't forget to keep this negative in front as well. Now we know that negative times negative gives us plus, so we would have 0.5 times 10 to the negative 7 plus 3, which is 0.5 times 10 to the negative 7 plus 3. That's going to be negative 4. But now the 0 cannot be k. 5 can be k, right? So we need to move this decimal place right after the k. So we're moving it 1 unit to the right, meaning that we need to, again, subtract 1 from the existing power of our 10. So we would have then 5 times 10. Negative 4 minus 1 is going to be negative 5. And this is how we end this example. So that's going to be 5 times 10 to the power of negative 5. And that is it. That's all you need to know about the scientific notation, how to convert from scientific notation into scientific notation, how to do multiplication and division. Thank you.